Good morning, good afternoon, everyone, from the International Society in Quantization, Geometry, and Dynamics. It is my pleasure to introduce today's distinguished speaker, Professor Ucheli. Professor Ucheli is an assistant professor in the Department of Mathematics at the University of South Carolina. His research lies at the intersection of transport information geometry, data science, and artificial intelligence, and broader areas of modern applied mathematics, including stochastic dynamics, scientific computing, and computational analysis. He received his PhD in mathematics from the Georgia Institute of Technology in 2016, following his undergraduate studies in mathematics at Shandong University. After completing his doctoral work, he served as a CAM assistant adjunct professor in mathematics at the University of California, Los Angeles from 2016 to 2020. Since August 2020, he has been a faculty member at the University of South Carolina. Professor Lee's research reflects a deep and elegant synthesis of analysis, geometry, probability, and computation. His work explores transport-based geometric structures, divergence measures, and curvature-related phenomena, while also engaging with emerging directions in machine learning and AI-driven mathematical modeling. Through his contributions, Professor Lee has helped advance modern perspective on gradient flows, stochastic systems, and computational optimal transport, connecting rigorous mathematical theory with applications across science, engineering, and data-driven disciplines. We are delighted to welcome Professor Ucheli as the speaker for ISQGD Distinguished Lecture number 14, and we look forward to his distinguished lecture on contemporary development in transport-based divergences and geometric methods.
Okay. Hello, everybody. It's my pleasure to be here. Thanks, Milner, for his kind invitation. It's quite a organized event. So today I will talk about some geometrical calculations on probability manifolds from reciprocal relations in master equations. So many of you may heard about this machine learning applications. I guess it's starting from 2000. If I remember correctly, 16 or 17, the AlphaGo, right? The machine can win human on the Go setting. Later on, this is so-called the generative adversarial networks. People can create different images using a primal Jules structure. Later on, they do the protein folding, and this is my area, and also this Bayesian sampling and Bayesian inverse problems. So I want to tell all these applications has a very direct connection to our mathematics community. In particular, when I work on this probability or this algorithmic theory, we want to do the convergence of the macro process. Okay, so of course, this is engineering area. It's not only the proof. We also need to use what you understand to design some algorithms. Or in reality, people just directly do it. They don't think about the property of macro process that much as we do. But I think there's definitely intersections. So this is what I call the AI inference sampling and gamma calculus. The gamma calculus is what I like a lot, to try to help this in the algorithm wise. So I'll give you some examples. Later I will move to the math directly. Okay, so we go back to this question hopefully in the future. Now the sampling problems means the following thing. So you have some domain. Let's make things. The domain is discrete. I say 1 to n. You give I give you a function. This function is just a vector because it's a discrete domain. So just a vector. So we want to sample. We want to create a macro process. We create some stochastic process. Its inverse distribution in the end will become the so-called Gibbs distribution. It's pi I equals 1 over z e to negative vi. Okay, I in the omega discrete sample space. basically omega is super sample space or status space. And this Z is super normalization constant. To do so, I mean, one of the simplest way to do it is so-called macro process, right? You can consider a discrete state. You can denote a probability function, like which is a vector, PIT, I from 1 to n. And then we can basically probability, we want to design a dynamical system, which is the so-called master equation, which is just like dpi over dt, which equals summation of j of qji pj minus qij pi. Okay, so basically it's a linear equation. Now you want to maintain the q here is what we call the probability transition function. Okay, so you want to design a suitable q. In the end, this the stationary solution of this linear equation will become your inverted distribution. And of course, there's a corresponding stochastic process behind this macro process. That you are not only using ODE to directly go to your solution point, you design a stochastic process to approximate your ODE, and the stochastic process will convert to, in the probability sense, it converts to your inverted distribution. So there are special case of this macro process, so-called detailed balance condition. The detailed balance condition means that there exists a suitable vector pi. This pi is your inverted distribution, such that your qji pi I will equals qij pi I equals qji pi j. And sometimes we use this graph, this weight function to denote it. Basically, we write omega ij equals omega ji, which equals qji pi j. Okay, of course, this is symmetric if you switch the index of I and j. So this condition is so-called detailed balanced condition. Once you have it, I give you one example, which is very famous, so-called metropolis Hessian's algorithm. Okay, given a step size 30 lambda than 0, we can consider in practice it's not only continuous time macro process, it is also a discrete time macro process. We consider discrete time update of the master equation. By the following update, basically you consider a suitable delta t of the step size. Given a specific conditional density QIG, this one QIG is something you can define. So then you can write down the following metropolis Hessian's algorithms. So you can verify. I mean, this requires a little bit of computation. You can verify this QIG constructed by the following way. The above way will satisfy this detailed balance condition. So basically, if I give you pi I and pi j, right, then I can write down metropolis Hessian's algorithm, okay, which satisfies this condition. So basically, if you can tell me what is pi, I can give you a macro process, okay? And of course, people are interested in why you use this way, right? Maybe I can design some other way, right? Because pi is given, there are so many different queues. So the algorithm in this area usually, like say, for which queue, I mean, it converted faster, and what, of course, we have also considered discrete time, but in discrete time sense, for what type of queue it converts to the inverted distribution as fast as possible. Now, once you talk about the convergence, the convergence speed, this is a typical algorithmic theory, right? You want to know the rate or what the dynamical system given by the above equation behave. Now, this is transport entropy and information and geometry coming in, okay? Because this is why we can use a lot of tools. I try to design different Leibler function. We can get different Leibler constant. We can do different, you can do analysis, so on and so forth, okay? So this is the picture given by one of my friends from Sony. It's the Frank Nielsen. He created this table. So there are many interesting distances defined on the probability simplex set. Okay, you can design the Euclidean distance. You can design the Minkowski distance, so on and so forth. Now on this side, there are so many, but I have to tell you one important one. I will use as a beginning point, which is so-called KL divergence, the Kullback Leibler divergence, or sometimes we call it relative entropy. Okay, one of my friends Like Amari also have his own divergence called Amari alpha divergences. But I think this one is the starting point. Once you understand this well, then we can think about general type. Now this optimal transport thing is also into this picture. This design is so-called the Wasserstein distance, or called the Mount Kotonovich distance, so on and so forth. So let's focus on the KL divergence. I can tell you a little bit how it connects back to this optimal transport setting, and then why, there are a lot of interesting maths and how this, sometimes go to the AI, to the algorithm side. Okay. Now let's do a very simple example. We consider so-called Leibler method to study the dynamic behavior of this PT from the master equation. We applied, we designed a so-called global Leibler for functional. Okay. I mean, depending where you're coming from. I'm coming from dynamical system. We just call any this divergence or called Leibler function. Okay, because it's a way to test what happens to your market process. It's just like very simple. It's a very simple function. Pi log pi over pi, and you take a summation. Okay, so this function is so-called PL divergence, and this function it is non-negative. Wherever p equals pi, it is 0. Okay, and you apply this, also you take the derivative of this KL divergence along the master equation. You get the following quantity by some linear algebra. Now you can easily to verify because it's the difference of log p over pi and difference of p over pi. So they are in the same sign. So you know it's non-negative. In literature, the KL divergence is called relative entropy of free energy in the statistical physics community. And this I, this function of I here, given by this difference of log and difference of p, we call it the relative Fisher information functional. Okay. Now you say, oh, you have some dissipation of KL divergence. It will tell you your p converts to pi, right? So from the linear equation, you can directly see it. So what can you see a little bit more? This is something this optimal transport, all these pictures are saying come in. Okay, so we are interested in the so-called Leibler constant. We are not only interested in the dissipation structure. We are math guy, right? We want to do more. So you want to do the correct analysis. So we try to get the Leibler constant from using this dissipation behavior. So roughly speaking, we are not using KL divergence as the Leibler function. We use the Fisher information as the Leibler function. So basically, you take additional derivative of KL divergence. Then there are some interesting, calculation to tell you what is the lambda. Okay, once you figure out this lambda, you can do the usual groundwork inequality by integrating on the time variable. Can prove the following exponential convergence result for the KL divergence. As a byproduct, once you can figure out this Leibler constant lambda, you can also prove this so-called the log Sobolev inequality on discrete domain. Okay, so here we call the log Sobolev in the following sense. The I is essentially the Sobolev term because you have the difference of terms, which in the continuum level it is the gradient. The log references log p over pi, so this is so-called log Sobolev inequality. Now in the literature, this is blow up everywhere already. Mathematically, I just review mathematically what we can know. Okay, in the more scientific viewpoint, the physical, chemical, and biological, this type of master equation or the related inequality or its related properties is very useful for modeling tools. And the information theoretical interest, basically, they are interested in this lambda really a lot. Okay, so to figure out this lambda, you will have some techniques. Okay, so it's a so-called iterative gamma calculus. Okay, basically, how do you compute derivative, right? I mean, of course, you just compute and estimate. That's the standard way to do it. But usually, there's some organization effect. You make the thing, more organized, so then you can figure out this lambda in a better way. Okay, so this is so-called Bakery, Emery, Otto, Villani. Flex Otto is the one of the leader in this field. The Villani is Cedric Villani is the Fields Medal winner, and the Bredon, the So this thing also relates to the so-called geometric calculation in the density manifolds. Okay, so once you understand this gamma calculus, then you look at this. So later I will talk this a little bit more. You can view this gamma calculus as a suitable way to compute this we call the Leibler connection in the density manifold. So the geometric computation in density manifolds is purely something we think it's like when you do the geometry, it's a standard thing. But this thing talk to how to you organize this derivative of the occurred objects. So this is also introduced by so-called Lafferty. Lafferty is also the chair in the Yale University working on this machine learning right now. So it's a statistics department. Flex Auto and John Lott is a geometer and giggly. So this is recently widely known and people try to really actively work on this area. Now, more specifically, it's so-called entropy dissipation and Harper causativity. It's a very hot area in mathematics. Arnold, Kala, and Jose, so on and so forth. So I skip the details here. I just tell you, in the AI side, this is also just playing this inequality or playing this KL Fisher information is also very popular. We have so many. It's not a full list. I just mentioned some representatives here. This statistics games, mean games, sampling, engineering. This is already blew up. It's not one area for sure. Now here I want to emphasize on discrete domain, which I will talk is EMS, Milky, and Shuni's group. We work on this a lot. And this lambda is so-called Ricci curvature and displacement convexities for the on the simplex set. Okay, so this is the thing I will talk today. So there are some other interesting application which I'm also part of it. So I will not give you detail. It's all related to this motivation. Okay, so then the rest is go to different directions. Yeah. Roughly, I think it's more than 40. I think more than 100 people in different areas. The experts more than 100 already. Okay. Now let's review what is the optimal transport. The optimal transport has several, as I said, it's a big area. There are several different formulations. Now in this talk, I only talk about the so-called marginal formulation. People call it the Benjamin-Brenier formula in 2000. So basically, it is you think of the following way: you design give you two proper distributions. You want to design a distance between two distribution. How do you design distance? You write it as the expectation of the vector field squared, and then you for each x you consider as a vector field x dot equals vt xt, and x0 is equal to rho 0, x1 equal to rho 1. Okay, so you want to connect rho 0 to rho 1 to dentists by the expected kinetic energy squared. So this is the idea. Now essentially, if your density is given by 4 and given by 1, okay, 4 is the represents the probability density function. Okay, suppose it's an image. Now this is the geometric look like by solving this minimization problem. Okay, approximately. John Lafferty gave a talk on this. So he define this distance and its underlying structure called density manifold. Once we talk about the manifold, we are talking about asymptotic behavior, which means if rho 0 and rho 1 are really close to each other, what does this distance tell us? Okay, so it turns out to be the so-called optimal transport metric, or some people call the Wasserstein metric. Okay, so this one is the way to it's a length space description of a distance function. Now this is the way to define so-called metric. Metric is a asymptotic behavior. Basically, you let rho 0 and rho 1 to be really close to each other. This is so-called autocalculus in the now recent literature. So it's very simple. You define a suitable metric. I call rho 1 dot rho 2 dot as the tangent space vectors. And then you define the so-called, this is like a negative divergence rho gradient inverse. So basically, it's h negative 1 rho norm, h negative 1 type of metric. So if rho is, if there is no rho here, it's quite simple. It's just h negative 1 metric. But if we have a rho, it is not, it's a rho dependent metric. right? So you have a rho dependent in this setting. So you can write a rho I dot by this operator again, negative divergence rho gradient of phi I, and then you can write it into the cotangent form, which means it's gradient phi 1 gradient phi 2 times rho times dx. So here, for this boundary setting, this is a little bit what do we mean by this operator? This operator you either define on a torus or you define on RD. Okay, so in the infinity part you don't have the term. Okay, so basically we allow to use the integral by parts freely. The boundary term will be dropped. So this is a simplified thing. This is the original autocalculus. Now, everything here is continuous level. So it's an infinite dimensional Riemannian manifold for this metric. And for this infinite dimensional manifold, you probably can design a lot of inflating properties. You can compute the curvature, you can compute the gradient flow, you can compute a lot of inflating. People already work on this for more than 25 years. Okay, so it's very fruitful area. But now let's work on discrete area. The discrete means I have a simplex set. Remember, we have my problem is discrete, so I want to have a vector. We call it the probability vector, which is just on the simplex set. Summation equals to 1, should non-negative. The time space here is trivial. It's just like summation of sigma I equals 0. Here we only consider the interior part. Okay, we don't consider the boundary. Then we can define the so-called graph notation to represent this function. The graph notation is very easy. Consider weighted graph J equals the vertices H and it's omega. So basically you can define a discrete divergence operator and discrete Laplacian operator and discrete gradient operator. Okay, so just take differences. So everything is well defined. I skip detail here. This is something very tricky. But the major issue to define a discrete Western metric is so-called as Onsaga's response matrix. So you have to design a weight function. This is a weight function defined to represent, remember, in the Western metric in continuous level, it's a divergence rho gradient. You have additional rho to be defined in that operator. Now, in the discrete setting, you have to design a suitable rho on the edge set. So this is what we do. So you have this theta ig equals theta pi over pi I, pj over pi j. Now you want theta ig to be symmetric. Now you want to define a matrix function is a negative divergence omega on discrete divergence operator, theta and discrete gradient operator. Now theta times gradient of phi will become theta ig times gradient omega phi ig. Okay, so essentially speaking, you have additional weight function is p dependent. That's it. Okay, so remember this is the continuous level. You have the rho dependent elliptic operator, right? Now you want a discrete version for this. Okay, this is also in the numerical setting we call the eliminator function. So this is not only in the math process, in the numerics algorithm, it's always you have this theta function. Okay, in machine learning we have a fancy name for this theta. We call it activation function. It's behaves the same way we use, because as long as you approximate your equations, this thing will, in some format, you will see it. Now, once you have it, we can design so-called discrete autocalculus or discrete Wasserstein metric. Now, basically, give you a simplex set. I'm not interested in the Euclidean metric on the simplex set, right? I'm interested in something depending on this operator, okay? Divergence, theta, and gradient. So what do we do? It's very simple. You design a metric by v phi 1, v phi 2, which is v phi 1 equal to r theta, v phi 2. So r theta is essentially L theta pseudo inverse. Okay, so essentially it's the discrete version of negative divergence rho gradient inverse, right? Because that one is not really invertible if you really think interdimensional. Similar here, but this is a discrete version of the weighted graph Laplacian inverse. Okay. Anyway, you can write it into the cotangent form, which means you write L of theta, which is r theta pseudo inverse. Then you write the negative divergence of theta gradient. then you will have the following. I mean, interdimensional is just the operator sense, and the infinite dimensional become matrix multiplications. Okay, so you will have the 1/2 summation Rj in E greater than omega phi 1 greater than omega phi 2 and theta Rg. Okay. Now, once you have this formulation, we can define the so-called the gradient operator in the simplex set. Okay, gradient operator is quite simple. It's nothing but this response matrix. I mean, this metric times a metric inverse times this Euclidean gradient of this function. So we have negative divergence omega theta greater than omega greater than p of f of p. Okay, so I have to make a little bit of comment here. This is all the linear algebra operation. This is the classical Euclidean derivative of your function. Okay. Once you have this, we can do a good exercise to see how it connects back to our master equation. So you let f of p equals f divergence. Let's say f equals z log z minus z. So this is essentially KL divergence. You can design theta as follows. By some linear algebra, you will essentially get this linear master equation. This is what you have. This is somehow mimic this autocalculus for this Fokker-Planck equation, but here we work on the discrete version. Okay. Okay. So then you can design the so-called first order calculus, first order autocalculus. Basically, it's the entropy dissipation in the following way. You compute your KL divergence, you get a negative, the KL divergence transpose times the matrix times this gradient of KL divergence. Now, if you write it carefully, you get the gradient log difference of log p squared times theta. Theta is essentially the weight function. Okay. So if you look at the Fisher information at the beginning, you have different log times different p. Now it becomes different log squared times something weighted by this. We call this average function. See. Now you can represent everything into this so-called a master equation of the Osaka gradient flows. Essentially just like a metric times the gradient, and you have the dissipation. Okay. Now you can also define the distance, which is by once you have norm, the distance is the arc length. Give you any curve, you can define the arc length of this curve using this metric tensor. Or you can define the so-called minimal arc length problems. Okay, basically you try to take the inf over all the passes for the definition of arc length. Okay, you can also define the distance, so on and so forth. Now this area has been also been studied for I have to say more than 15 years. Okay, so it's 2011. The people already like Shuni, like Milky and EMS. So they already have been studying this for a while. So this is well understood. Now, what do we do here? We try to do a little bit more. Okay, let's compute this geometric calculation here. Okay, so let's consider a very general choice of theta function, because this one also have a lot of application, in particular in the AI algorithms, which I will. I don't have time to talk this time, but it will have a lot of applications. Basically, we try to design theta function, theta or either QID or the general theta function give you the energy. So as long as you can make the pet as the universal distribution. So this is some applications in this area, and I have a fancy name. This is not a math part. Okay, this is like a linear part. We call it the Wasserstein universe. Okay, every corresponding application is part of you either pick theta discretely or continuously, right? So you pick the Q, right? Really depends on application you are interested in. So it's right. It's such a big area. Now, what do we want to do? We want to introduce a generalized alpha or gamma calculus for stochastic systems from master equations. So it's a gamma calculus for generalized vector space on discrete state spaces. So what do we do? We try to compute all the quantitative, geometric quantity in this space. Okay. Now in this work, I follow the framework of Lot, which he introduces very beautiful notations. But what he computed is in the the density level, which is the continuous density level, I compute in the discrete level. So this computation is the more linear algebra, and we use more linear algebra than what lots of people use. So, but you can see there are a lot of different organizations for this curvature and terms. Okay. So number one thing, we have to define the directional derivative once you have a metric. So you compute this gradient times L theta times phi, and you can define the so-called this is the directional derivative of the theta along the direction. Then you can define the so-called communicator. Communicator just like two directions you acting on the same function. Okay. Now remember, your Laplacian matrix depend on the current point. So whatever you compute, you have more linear algebra involved, because once you compute the communicator, you will have two Laplacian matrix combined together, right? So your beta function is the other Laplacian operator. Your metric is the Laplacian operator. This is two Laplacian of Laplacian. You think this way. So it's quite interesting linear algebra behind it. Okay. Anyway, now then you write out so-called the gamma 1 operator. I call it gamma phi 1 phi 2, which is greater than phi 1 greater than phi 2 times partial theta partial pi. And then you can organize the Leibler connection by a communicator plus L theta of the gamma 1. So Leibler here is the key to understand, as I said, to understand the dissipation of the energy, because once you understand how it's organized, then you can modify it quite easily, and you have a lot of different ways to estimate the rate. So, Leibler connection, you can purely write it into the gamma calculus. So, as I said, you have two Laplacian. So one Laplacian, you can believe is one gamma corresponding to one Laplacian. Okay, you write it into a bilinear form. Now, if you do it for Leibler, you have two Laplacians. So then you have two gamma operators. So this is so-called, in the vector language is so-called iterative gamma 1. So roughly speaking, before I let you look at the details, roughly speaking, Becker-Emery calculus, let's only talk about gamma 1. It is iterative. You have the iterative gamma 1 calculus. Okay, in his, his paper is fully in the French, but essentially he also mentioned this, but he don't realize, according to this language, it's essentially gamma 1, essentially the Wasserstein Leibler connection. Of course, it's weighted by some theta function. Okay. If you only consider gamma 1, you don't consider theta function, but with theta function, that's the Leibler time. Okay, this is a beautiful, really beautiful computation here. Now then you can do the so-called parallel transport equation. Once you have a connection, the rest becomes standard. You just follow the Leibler time. You can write down all the equation you want. Give you two curves, okay, parallel along the curve. Then you can write down this parallel equation. It's a set of ODEs. Now, if you let let's say eta and gamma are same, then you will write down this. This is what I write here. But eta and gamma is eta and phi are same. This is the cancel. So you only have one equation. That's called the generative equation. Okay. So this is standard in the. It could actually follow what a lot in his paper. Okay. So it's standard. Right. This is so-called the continuity equation. This is so-called Hamilton-Jacobi equation. Okay. So you can see all these optical transport dynamics naturally in following Leibler connection. Now, of course, we're interested in the so-called Hessian operators. Hessian operators somehow relate to this derivative of your KL divergence. Okay, the second order derivative of KL divergence. By a little bit of computation, this is just standard in the geometry. You just write it out, write the Leibler connection. Then you have this formulation, and then using the detailed gamma calculus, you can represent it out. Okay. So it's basically the iterative gamma 1 with the additional term of the f. Now here there are some more magical things. If you are familiar with the continuous density level, there are some change of variable there. That's the original people call autocalculus. In discrete level, it's different, but with a very similar flavor. But because you have a theta function, you have the additional more term to handle with. So in the algebra, I mean, if you only look at the algebra wise, it's quite interesting to see what's going on here. Okay, and of course, this thing works for any energy function. So there's a lot of interesting detail behind it. Okay? Recently, I have worked with my colleague here in South Carolina. We have a strong group in the spectral graph theory. So in this setting, it's a lot to do with spectral graph eigenvalues. Okay, okay, I don't give more detail here. There are a lot of interesting things just behind the Hessian operator. Okay, if we estimate the Hessian operator, we have more interesting result. Can see here. Now this is the major. Okay, now we are ready to talk about the major term, which I call the remaining curvature tensor. The curvature term is a little bit more heavy because not a Leibler, it's a derivative of Leibler. And the Leibler times together, right? You have particular. If you, I mean, of course, we can directly use this. There's a very general formula for the curvature tensor, right? Directly in Wikipedia or in the book. But it's not exactly match here because you want to get something. Because my metric is graph Laplacian dependent. I want to know how many Laplacian operators here and how can we organize them well. But roughly speaking, if your metric depends on the Laplacian matrix, your Laplacian will be two Laplacians, right? So your curvature will be three Laplacians. Now, as I said, the Laplacian is the gamma. So you will have the so-called the third order gamma calculus. Okay, so I will show you later. So, but essentially, if you follow the definition, you can write down what is going on. You have the additional directional derivative, and you have this what I call the M matrix. It's some organization of additional directional derivative. So essentially, it becomes a Laplacian matrix of this M, and you take this gamma operator with L and with this commutator. Now this M is a Laplacian of Laplacian. So that's the interesting thing. So essentially, if you write it in this matrix form, it will define so-called gamma 3 operator on discrete domain. Gamma 3 means you have one gamma, and you take this. So this is one gamma, this is the other gamma, and then you do it again. So 3 gamma. Okay, you do it iteratively 3 times. This is what I believe in this. What our math can do. Okay, for the engineering guy, only just one gamma, I think this is enough for them to give a story, give the numerical experiments. But if you really want something deep, really want something on Euro, what you really need to estimate, you at least do it 3 times. That's gamma 3. Anyway, at least twice you get the Hessian, and 3 times you get this curvature. Anyway, so you have this gamma 3, and you have all this, this is some linear computations. And then you can represent the curvature formula. So it's not that simple. I don't give you full details here. Okay, you just check linear algebra here. It's not that obvious when you see it. Okay, we have to organize this wheel a little bit left. Anyway, so but this is what is it? Okay, so it's not easy to do estimation directly. But roughly speaking, it is a fourth order polynomial in the simplex set. It depends a lot on graph Laplacian matrix. So whether it's positive, whether it's negative, or what can we use this curvature formula to understand the dynamics, that could be the future work. Okay, but as I said, because of so big is the motivation, this curvature, if we can estimate the wheel in the future, I think this is really good for the algorithm design point of view. Anyway, so this is the formula. The major term I tell you it is second order derivative of theta function with the gamma 3 operator. And of course some gamma 1 things. Okay. I give you some examples before you are more confused. I give you some examples. Number 1 is called the chemical monomolecular triangular reactions. This is something really standard in the chemical book. You give ABC 3 state, their reaction. So basically in chemistry, people care about the mass equation. This is the most direct applications at the beginning. There are three bases, and their response matrix given by follows. It's a very simple graph Laplacian matrix. The only thing new here is the theta function, right? The theta is given by this, we call the logarithm mean I defined before. Now you can write down this Wasserstein connection. Here, it's quite symmetric. So here I don't give any estimation here, it's just a connection, a formula. Then I work on so-called a 3-point lattice graph. Now, 3-point lattice graph makes the computation much easier. We don't need to go to this gamma calculus compute. We can directly write down the graph Laplacian matrix. Because it's so simple, it have a so-called the cumulative distribution coordinates. Okay, this one will make your metric become diagonal. This metric is very hard to do, right? Because not a diagonal matrix, so it's tridiagonal. So you must go to this gamma calculus to do it. And now you can write it into the cumulative distribution function. There's a one-to-one correspondence. All the geometric quantity doesn't depend on the coordinates you are using. Okay. You can use what do we mean by cumulative? It's very easy in discrete. It's just x1 is p1, x2 is p1 plus p2. Cumulative distribution, right? Of course, x3 will become 1. It's p1 plus p2 plus p3, right? So, so basically, your simplex set will become x1, x2 space in this 0, 1 squared. X1 will be less or equal to x2. So it's half. It's half squared, right? It's just still triangle. And in this setting, you can use this metric operation. So in this coordinates, the metric will become diagonal matrix. It's 1 over theta 1 and 1 over theta 2. And the off diagonal term will become 0. Now, in this setting, you can compute your curvature directly. Here, I give you this is a sectional curvature. I give you the Ricci curvature. I give you a scalar curvature. Okay, so you have 3 curvature. I mean, this is requires a little bit of computation, but it's doable. Okay, so using theta function, we can understand what's going on for the curvatures. Now, you see, the number one question will say, oh, is this the Western space you defined is positive curvature or negative sectional curvature, right? Eh? Quite easy to do, okay? So, of course, you plug in this formula and with different theta function, with the different energy function you are interested, basically polynomial function or logarithm function, and you compute. And once you compute, you can do the design of the numerics. I do it by my MATLAB, okay? Then you can figure out, you can get a different curvature formula. And this curvature, I tell you, it's not that well defined on the boundary set. Okay, so let me tell you how to look at this figure. So once you look at this figure, it's on the x1 and I call it p1, p2. Under the p1, p2 will less or equal than p1 plus p2 will less or equal than 1. Okay. And then once you look at it, wherever p1 is close to 0, your curvature will become negative infinity. So it's the curvature not well defined on the boundary of the setting. But overall, it's all negative from the thing here. Now, it really depends on how you pick the alpha formula. The different divergences will really depend on how you define the theta function. Will give a different value of your curvatures. Okay, so this is what I said, that when you pick the theta function, all the algorithm to pick the theta function, the theta function will be the curvature. Now, at least from this angle, once we have the curvature formula, we can try to use it to indicate some properties for this space, for different Western space, right? We also do it for the geometric mean. This mean is quite nice because in this mean, we can compute the theta function, the curvature function in a really nice form. Now, if you are a little bit familiar with information geometry, it's 1 over p squared, which is the third derivative of the entropy. It's very natural here. Okay, so this so-called Amari tensor for tensor. So Amari tensor talk with the Western curvature in this geometric mean. This is really beautiful. Okay, so once I get this formula, I'm so excited. Okay, what I learned from this bigger figure, finally in one curvature formula, they talk to each other. However, Wasserstein have more structure. You have P1 times P2. Okay, this thing you never see it in the information classical information geometry because they don't have this, this theta function as I thought. Okay, their metric is just purely coming from the diagonal matrix of which is the Hessian operator of your calculus. Okay, so this is something beautiful. So you have something we know, American stuff, and something we don't know, one or P1, P2, one or P2, P3. Okay, and it's so simple, right? Look at it, it's so simple. It's a polynomial function. And then you can also estimate the curvature formula. Okay, of course, it depends on the choice of beta. As I said, if beta is one half, which is the classical Wasserstein metric, beta is 1/2, it is lower left. So you get all the curvature negative. This is unfortunately always the case if your consider classical optimal transform metric, the curvature is negative, the sectional curvature is negative. Okay, in discrete domain. Okay, now this is what we have. Now, if you pick a different beta, you can get a positive curvature. So basically, how do you pick beta, or how do you pick this activity function theta is really the key. Okay, nobody in application tell you how do they pick theta. They have motivations, but now we have a curvature as an indication to tell you which one give you what type of properties. Okay. Now, before I finish, I talk about my last topic is so what? Once you have curvature, right? Someone asked me like, so what? You compute curvature. Curvature is the one key to understand the stochastic process in that space, right? For the Brownian motion, rigid curvature tell you how this, the Brownian motion in that space goes, right? The convergence rate. Now, this is what we call the Western diffusion of graphs. What do we mean by Western diffusion? We are not consider the ODEs for master equation, the ODE in property simplex. We want to consider stochastic different equations. Okay, so we are usually in the so-called we want to build a canonical or maybe the overdamped Lagrange dynamics in the simplex set. It have a name called the Western diffusion. Okay. Of course, Western diffusion is in the infinite dimensional space is too complicated. We consider finite dimensional version. So what do we mean? You consider this invariant distribution. I mean, this finite dimensional Riemannian manifold is everything canonical. Okay, you define in the following way: you define the volume form, you define the this e to negative 1 or beta of some function. This is what we call the Gibbs distribution. Then you compute this diffusion process. So basically, this is your gradient dynamics, which is and this the additional term with graph Laplace and Brownian motion is what we call Wasserstein diffusion. Okay. Now your curvature, if you have an estimation of a curvature, in particular Ricci curvature in simplex set, you can understand this SDE quite nicely. And this SDE, as I said, has a lot to do with the application side. People call the stochastic dynamic density functional theory. And this is the machine learning people care about how to do sampling distribution of simplex set. So it's a universal application. Once you have the curvature, you try to design some SDE with nice properties. I just organize this beautifully, okay? Because once you have graph Laplace, you can organize them with this linear algebra, okay? So I organize individual noise and the rest is the common noise, okay? Anyway, so this is my talk. Here I'm still working on here. There's a lot of to do once you work on more general graph, how the curvature behave, how does it tell you this SD or this kind of equation goes. Anyway, so we'll continue to estimate the curvatures for Wasserstein on Saga time metrics. So this just means theta function, as I said. On general graphs, we try to understand the convergence analysis for Dean Kasawaki dynamics on general graphs. We want to construct the convergence guaranteed AI sampling algorithms on discrete domains. Okay, thank you for your attention.
Thank you, Professor Lee, for your wonderful presentation. Let me stop the recording, then we can ask for questions You can use it.